Good evening. Welcome everyone. We are discussing problems of mapping. In previous class, I have solved 10 problems of mapping. They are of board standard. Today, through this video, I will solve some problems of mapping. They are important for board as well as competitive also. So problem number 1. Let a minus 1 to plus 1 and if a to a be a function such that fx equals to x into mod x, so that f is bijection, that is 1 1 1 2. So fx equals to x into mod x. We know this is x square if x greater than equals to 0. For greater than 0 it is x into x. So this is minus x square if x less than 0 or less than equals to 0. So first we prove that it is 1 1. Let so greater than 0, but a equals to minus 1 1. So we can take it, that is this one is minus 1 less than x less than equals to 0, and this one is 0 less than equals to x less than equals to 1, because a is given minus 1 to plus 1. Now draw the graph of function fx equals to x square, x greater than equals to 0. So this is parabola fx equals to x square. So y equals to x square, x greater than equals to 0. And it is, if it is 1, suppose this is 1, so maximum you have to write this one, y equals to x square. And x square, x square equals to minus y. So figure is this type of parabola. But due to presence of less than 0, this part is absent. This is 1, this is 1, this one also minus 1, and this is minus 1. So figure y equals to minus x square. So at x equals to 1, y equals to 1, at x equals to minus 1, y equals to minus 1. So to prove this result, this is 1 1, we use concept of graph. Look, for if we draw a horizontal line anywhere, if we draw a horizontal line, cuts it at only one point, so it is not many one. So any horizontal line cuts it at only one point. Therefore, it is not many one. That is 1. That is 1 1. So f is 1 1. We can also prove taking x1 x2 belongs to 0 to 1, fx1 equals to fx2 implies x1 equals to x2. So we have already solved many problems using this concept. Here we are using concept of graph. So this one is 1. Now range is -1 to +1. Look, range, if we draw the graph, we look the graph, what is value of y? -1 to +1. -1 to +1. And what is codomain? Codomain. This is also -1 to +1. So range equals to codomain. Range equals to codomain. So f is 1. So f is 1, 1, 1, 2, hence it is bijective. Hence it is bijective. So using concept of graph. Or you may use the previous one, take 2 points from domain x1, x2 and prove that if fx1 equals to fx2, then x1 equals to x2. Now, problem number 3. We are considering problem number 3. A PART4 defined by fx equals to x cube plus x is bijective. We have already solved this problem for x cube plus constant, but this is x cube plus x. So let x1, x2 belongs to R, that is domain. So fx1 equals to fx2 implies x1 cube plus x1, x2 cube plus x2. So x1 cube minus x2 cube. So x1 minus x2 common. And this is x1 square, x1, x2, x2 square plus x1 minus x2 equals to 0. So x1 minus x2, x1 square, x1, x2, x2 square plus 1 equals to 0. Then we are getting two options. What are the options? x1 minus x2 equals to 0. This implies x1 equals to x2. Now, to make it 1, 1, you have to prove this is non-zero. So, or x1 square plus x1 x2 plus x2 square plus 1 equals to 0. Now, try to express it in terms of square term. A square 2x1 plus x2 by 2. So 2x1 x2. So x2 square plus 1 plus x2 square minus x2 square by 4. To make it perfect square, we have added this. So subtract it. So x1 plus x2 by 2a whole square plus 3x1 square by 4 plus 1 equals to 0. This is square term, this is square term, this is constant. So, which is not equal to 0. Since x1 plus x2 by 2 whole square greater than equals to 0, x1 square by 4 greater than equals to 0 and 1 greater than 0. So this option is not possible. So what is the only option? x1 equals to x2. Therefore fx2 equals to fx1 implies x2 equals to x1. So f is 1, So listen, we have already discussed this one. We are getting two options. So to make it 1, 1, x1 equals to x2. So this option is possible and other one is not possible. So this is the reason why it is not possible. It is positive, positive, positive. So it cannot be 0. So this is first part, 1, 1. Now we prove that it is on 2. So for now for on case 1, K belongs to N, codomain. Codomain. K belongs to and K is even. K is even. If K is even, then K minus 1. K minus 1 belongs to N and K minus 1 is odd. And K minus 1 is odd. So what is f of K minus 1? So K minus 1 is odd, so we get relation from this one. So N plus 1. So K minus 1 plus 1. So K. So f of K minus 1 equals to K. So range equals to codomain. So case 2, K is odd. K is odd implies K plus 1 belongs to N and it is even. And it is even. So what is fk plus 1? So it is even. Even means this one. So k plus 1 minus 1 equals to k. So in this case, fk plus 1 equals to k. So range equals to codomain. Here also, f of k minus 1 equals to k. So range equals to codomain. Codomain. When case 1, when k is even. When k is odd, then also a range equals to codomain. Therefore, f is on 2. F is, we have already proved, f is 1, 1. So f is 1, 1 and 1, 2. Hence it is bijective. Hence it is bijective. 1, 1 and 1, 2. Hence it is bijective. So this is most important problem. Now problem number 2. We have already discussed this type of problem in problem number 1 with the help of graph. But for this, graph is not simple one, so we would generate one. So fx equals to x by 1 plus x greater than equals to 0. So x by 1 minus x less than equals to 0. But look, this one, and the range is minus 1 to plus 1. So this is function. So domain is R for greater than 0 and for less than 0. So to prove it is onto. So let x1, x2 greater than equals to 0. So fx1 equals to fx2 implies x1 by 1 plus x, because for greater than 0, so x2 by 1 plus x2. So this implies x1 plus x1 x2, x2 plus x1 x2. So x1 equals to x1. So f is onto for this realistic sample. Now case 2, x1 x2 less than 0. So fx1 equals to fx2 implies less than 0. So x1 by 1 minus x2 by 1 minus x2. So x1 minus x1 x2, x2 minus x1 x2. So x1 equals to x2. F is 1 or x less than 0. Now case 2, this is case 2. So case 3, now case 3. Case 3, x1 greater than 0 and x2 less than 0. Then fx1 equals to fx2 implies x1 greater than equals to 0, suppose. So x1 greater than 0, 1 plus x1. fx2 for less than 0, x2 by 1 minus x2. Now if x1 greater than 0, x1 by 1 plus x1 is positive, and if x2 less than 0, so this is always positive. For x2 less than 0, so x2 less than 0. So x2 less than 0, x2 by 1 minus x2 equals to negative, equals to negative. Negative when, look, x2 equals to half, then x2 equals to minus half, x2 equals to minus half, then this one is negative, minus half, this one is negative, and 1 minus x2, this is positive. So it is negative by positive equals to negative. So which is not possible? This one is positive, this one is negative. So which one is not possible? Similarly for case 4, what is case 4? x1 less than 0, x2 greater than equals to 0. You can take less than equal to also. Then x by less than, x by 1 minus x, x1 by 1 minus x1. So greater than 0, x2 by 1 plus x2. Here also this one is positive, but this one is negative. So LHS is negative and RHS is positive. So not possible. Not possible. So what we are getting? So we are getting fx1 equals to fx2 implies x1 equals to x2 in case 1 and case 2. And case 3 and case 4, it is not possible to verify. So we discard this case. So f is 1, f is 1. So f is 1, 1. So we are getting f is 1, 1 function. Now we have to prove it is onto. It is onto. For on, let k belongs to -1, 1 for domain. So case 1, -1 less than k less than 0. So k by 1 plus k by 1 plus k. So k, this is negative, and 1 plus k is positive. 1 plus k is positive. So this is negative. This belongs to less than 0. Therefore, f of k by 1 plus k negative. So this one, for negative case, k by 1 plus k, 1 minus k by 1 plus k. So k by 1 plus k is LCM, this is 1. So range equals to codomain. Range equals to codomain. Now case 2, if 0 less than k less than 1, then k by 1 minus k is positive, 1 minus k is positive. This is positive, that is greater than. So f of k by 1 minus k. So for greater than 0, so this formula, k by 1 minus k, 1 plus k by 1 minus k. So k is 1 minus k is LCM. So this is k. K, 1 minus k plus k cancel. So this is k. So k by 1. So k. So range equals to codomain. Range equals to codomain. Here also range equals to codomain. Case 1 and 2. So f is on. In case 1, if k by 1 plus k is k. In case 2, k by 1 minus k equals to k. So range equals to codomain. F is on. Therefore f is 1, 1, 1, 2. Hence bijective. So this is not important for board, so you may omit it, but it is simple. Next, now I consider 5, 6, 7, 3 more problems. So problem number 7. So that if R0 means set of real numbers excluding 0. This is R0. R minus 0. Defined by fx equals to 1 by x is 1, 1, 1, 2. So is f into R0 is 1, 1, 1, 2. So this is very, very simple problem. So let x1, x2 belongs to R0 domain. So first part is very simple. fx1 equals to fx2 implies 1 by x1, 1 by x2. So x1 equals to x2. So So f is 1, 1. Now for on to, let k belongs to R0, codomain. So fx equals to k implies 1 by x equals to k. So x equals to 1 by k. So fx equals to f1 by k. So k. So fx equals to k. So f is 1. F is 1. So f is 1, 1. So this is first part. Now second part. So this is n to R0. So let x1, x2 belongs to n domain. Fx1 equals to fx2 implies, so x1 equals to x2, so f is 1, 1. F is 1, 1. So first part. Let k belongs to R0 codomain. So fx implies 1 by x. 1 by x equals to k. So x equals to 1 by k. X equals to 1 by k. Now if k equals to 2, it is half. So does not belongs to n. Does not belongs to n. That is, preimage of k is not natural number. So you are not getting, it is not natural number. So it is not onto. So f is not onto. So it is 1, 1 but not onto. So we have already discussed this type of problem. This is very simple one. Now problem number 5. So if n to n defined by fx equals to this, prove that f is many 1 or 2. So many 1. So our main aim will be two different elements have same image. So if n plus 1 by 2 n is odd. So correctly n is odd. This is even. And this is even. So correctly this is odd, this is even. So f3, this is odd number. So 3 plus 1 by 2, this is 2. Now f4 equals to even. So 4 by 2 equals to 2. So 3 and 4 have same image. So f is many 1. So first part is very simple. F is many 1. Now for on or on. N equals to odd. Equals to 2k or on to let k belongs to codomain. K belongs to codomain. K is odd implies 2k minus 1 is odd. So if 2k minus 1, so 2k minus 1 plus 1 from this rule by 2, so k. So range equals to codomain. So K is even, implies 2K is even. So f of 2K equals to 2K by 2 equals to K. So here the range equals to codomain. Therefore f is 1, f is 1, 2. So f is 1. F is many 1, f is many 1, and f is 1. So for many 1 example sufficient. Next 6. One mapping. 1 mapping from, so number of 1 mapping. 1 mapping equals to, this is 3. NB P NA. So 3P3 equals to factorial 3 equals to 6. So number of 1 mapping. So A 1, 2, 3. B 1, 2. So this is 1. Then A 1, 2, 3. B 1, 2, 3. So 1 is fixed. 2 to 3, 3 to 2. This is case 2. Then A 1, 2, 3. B 1, 2, 3. So 2 is fixed. 1, 1. 2 is fixed. 1, 3. 3, 1. Then you calculate in this way and you are getting how many mappings? 6 mappings. 6 mappings, 1 mapping. You have to find those mappings, those 1 mappings. So you are getting how many? 6. From this formula you have to calculate 1 by 1. So today, through this video, I have solved some more problems of mapping. So for board as well as JEE main and WB JEE also. So you solve these problems and I am sure that you get at least 1 4 marks problem from the chapter mapping. Thank you for today.